In the previous video, we talked about fixed points. So fixed points are points where if you apply the map f to a fixed point P, you end up back at P. And then we mentioned that you could have stable or unstable fixed points, sinks or sources. Question is, can you identify just by looking at the map f whether your fixed point will be stable or unstable? And that's the topic of a very nice theorem, which tells you what you need to do is look at the value of the derivative of your map at a fixed point P, and then look at the magnitude. And if that magnitude is smaller than 1, then it turns out that you have a stable fixed point, a sink. If the magnitude is bigger than 1, you will end up with something unstable, a source. And then you might wonder what happens if my magnitude is exactly equal to 1. Well, then obviously the fixed point will still be either stable or unstable, but the theorem that we're going to show you today will not be able to help you here. So in that case, you need to be a little bit more creative to figure out whether you're dealing with a sink or a source. Now in this video, we're only going to prove the first case about a stable fixed point. The unstable fixed point is left as an exercise, so there's a different video about that. Okay, let's get started. The first thing we're going to do is look at this expression over here. Pause the video and see if you can write this expression over here as some sort of limit involving neighboring point x that move towards our fixed point p. So this is basically just applying the definition of derivative. Okay, so we know that if we take the limit of a point x, which is close to p, and we bring it ever closer to p, and then we look at the limit of f of x minus f of p, and we divide that by x minus p, and then we take absolute values, then basically what we have is the magnitude of the derivative at the fixed point p, obviously, right? Okay. Now in our case, we're proving the first part of this theorem here. We know that this thing is smaller than 1. So that's a number smaller than 1. The nice thing about real numbers is that you will always be able to squeeze in an extra number in between here. So we can write down that this will also be smaller than a number a, which by itself is also smaller than 1. And it will turn out later on that this a will play an important role, the fact that a is smaller than 1. Okay, let's take one step further. Let's just consider this left-hand side here as a function of x, so g of x, okay? And then the question is, do you know something about the behavior of that function g of x, and more specifically whether or not it's smaller than any of these numbers here, and in which region it should be smaller than any of these numbers? So pause the video and use what you know about this function and how it behaves in the neighborhood of p to try and answer these questions. Let's make a little diagram to make it a bit more concrete. So we have the y-axis and the x-axis, and we're dealing with a fixed point p. And we're interested in plotting our function here that approximates the derivative, g of x. We know if we evaluate g of x exactly at p, then we end up with the derivative, or at least the magnitude. So this will give us this value over here. Excuse me. So we know that this value f prime of x is smaller than 1. And we also know that we squeeze in another value in between a. So this is also smaller than a. Now I haven't mentioned this explicitly, but let's assume that we're dealing with very nice, well-behaved, polite functions. So if we take the derivatives and expressions like these, we end up with something that is nice and continuous. So our function g of x, we don't know exactly what it will look like, but we only know that it will move to this point here at p, and that it's continuous, so it might do something like this. I don't know, it could also do something like that. Doesn't really matter. But the important point is that as long as you're close enough to your point p, you see that you're still in a region, because of continuity, where you will still be smaller than this horizontal line here, a. So there will always be an absolute neighborhood around P. It could be extremely small, but that doesn't matter, such that for all points in that neighborhood, this function g that we evaluate here will also be smaller than a. Okay, so excuse me for my cough. So we know that there should be some sort of epsilon neighborhood, so there exists an epsilon, such that for all values in that epsilon neighborhood around our fixed point P, we have the situation that our function g of x, and let me just copy what that was f of x minus f of p divided by x minus p, that's some absolute value signs. So this function should in that epsilon neighborhood be smaller than a everywhere. Okay, interesting. So now the next step is, what can we do with this more particular? Let's not lose track of what we're interested in. We're trying to show that if you get in a neighborhood that's small enough around our fixed point P, and you keep on applying the map, that eventually you should end up at the fixed point P, because that was our definition of a sink. So the natural question to ask is, okay, let's start at a certain distance here from our fixed point P at a value x, and then apply the map once. And then the question is, what has happened? Will we have moved closer to P, or will we have moved further away from P? And the question is, can we use what we have over here to answer that question? So pause this video and also take into account that P is obviously a fixed point of our map here. So if we rewrite this a little bit by bringing the denominator here to the right-hand side, we know that if we evaluate the distance between f of x and f of p, and remember p is a fixed point of f, so f of p is just p, right? So this thing is smaller than a times x of p. And again, this is true for all possible values x that are in our epsilon neighborhoods of P. So this indeed gives us our answer. Why? Because what we have here, the distance between x and P, that's just how far you started out before you applied the map. And then on the left-hand side, you have the distance between f of x and P. So this is how far you are away from P after you apply the map. And what's the relationship between these two distances, between our original distance and the distance after applying the map? Well, this relationship is that this thing becomes smaller than our original distance multiplied by a number a, which crucially is smaller than 1. So this tells you that after applying the map, the distance to P shrinks. This is interesting because this tells us that we're moving closer and closer towards P. And this is actually the crux of the whole proof. This is the essential part here because it tells us that we're moving ever closer and closer towards our fixed point P. The only thing that we still need to do is wrap things up a little bit and make things more formal, but this is the essence of the proof. We keep on moving closer and closer towards our fixed point P. Next step is, of course, repeating that procedure and applying f yet another time. Question is, can you do something similar here, taking into account everything you know? So pause the video and see if you can take the next step here. So this statement here is valid for all possible x within the epsilon neighborhood. And we've just also figured out that f of x will have moved closer to P. So obviously f of x will also be part of that epsilon neighborhood, just as our original point x. What we can do is we can have that same expression, which is valid for all possible values of x, and just repeat that and replacing x by f of x, which is also part of the epsilon neighborhood. So if we do that, we end up with f2 of x minus p smaller than a times, excuse me, f of x minus p. Now, let's take a look at this thing over here. Well, we know if we look back at that equation over here, that that quantity by itself will also be smaller than a times x minus p. So if we combine all of that, the whole thing will be smaller than a prime x minus p. So this thing will keep moving closer and closer towards p, as you can see here, and it's no big surprise that you can keep on repeating that procedure forever, and you can write down something like, if you apply the map k number of times and you look at the distance from p, that this will be smaller than a to the k of x minus p. And remember again, a is a number which is smaller than 1. So what happens if you take the limit of k going towards infinity? Well, obviously, a to the power of k will move towards 0. So this limit will move towards 0. And this means that the distance between f and p will move towards 0 as well. So in the limits, if you apply the map an infinite number of times, you will end up at the fixed point. So we've shown that this is indeed a stable fixed point, a sink, right? Final bit of terminology is what we have called the basin of attraction of a fixed point, a stable fixed point, and that's just a collection of all the points x that it will eventually end up at the fixed point if you keep on applying the map an infinite number of times. So from the proof, we know that this basin will at least consist of a small neighborhood around our fixed point P, but this thing could be much larger in practice, and it could be disconnected. There could be other parts of the phase space that will eventually end up in the fixed point. So this is what's called the basin of attraction of our stable fixed point.